Okay, welcome back after the break. So we can get settled, then we can all get to our second lunch of the day very quickly. This afternoon, or this late afternoon session, we've got three more presenters. The first one is Tristan, who unfortunately caught COVID just before the workshop, so he's not able to be here in person, but I'm sure will give us an excellent presentation anyway. So he actually joined Randy Reed's lab way back when in 2016 and started working on ISOLDE back then. And about a year and a bit ago, moved over to Altos Labs, where he's continued to work on it. Now, as far as I can tell, 2016 is getting on for 8 years ago. So I'm not quite sure where the other 3 years went, but I'm sure we'll hear about that in a moment. So, Tristan, please take over.
Thank you. Thank you for the introduction. And yes, I am sorry I couldn't be here. I am feeling much better. I'm just very slightly COVID positive still. I think it's best to stay away from everybody. So as to the question, why 5? You'll notice on the abstract book, it actually still says 7 because I started in September 2016 on this project, but the first release of ISOLDE was 2 years later in 2018, which is why I decided on 5 years as the headline here. But actually, I was thinking back at it, I was kind of shocked to realize that it's really about 14 years now since I started down this path. And I figured for this talk, I'd start with a bit of a retrospective on where I came from and why doing this work was so important to me. Let me do this. Okay. So what led to ISOLDE? So back in 2010, I had no experience in structural biology whatsoever. I was a chemical engineering graduate who'd found myself into a wet lab biology group doing fairly classic biochemistry stuff, but with a bit of an interest in molecular dynamic simulations. And at the time, from that outsider's perspective, what I found was that the nuts and bolts of crystallography, how the sausage is made essentially, was really quite opaque to the end user. Generating maps really required specialist software, which tended to assume quite a lot of background knowledge. And even very few packages made it easy to actually view the models together with the maps that led to those models. And even fewer, really just the one at the time, of course, Coot, with a few people still holding on with O, really provided tools to diagnose and fix errors. And in the downstream community, of which I was very much one, there were some really, and there still persist, honestly, some dangerous and often never explicitly stated assumptions that essentially either the experimental model is the inviolate ground truth against which all simulations and all downstream modeling should be compared, or any residual errors in the experimental model are small enough to work themselves out with a long enough equilibrium molecular dynamic simulation. Now, high resolution, of course, as we all probably know, that model building at high resolution was and is fairly straightforward. When you have high resolution data that unambiguously positions each or most atoms, you don't really need many restraints. You can just place the atoms, as you know, the sequence of your protein. You can build it up, and things just sort of fall into place and stay there, constrained by the data. Now, this wasn't the sort of data I started with or stumbled my way into. What I started working on in a roundabout way was the 3.8 angstrom crystal structure of the insulin receptor. And of course, at the time, I had no idea of even how to generate an electron density map from structure factors. So I had no way to see the model in its density. And from that outsider's perspective, I distinctly remember thinking, well, 3.8 angstroms, 3.8 by 10 to the minus 10 meters, that's tiny. That model must be pretty good. And of course, that is very, very far from the truth. The problem with 3.8 angstrom resolution is that, of course, you get down to there, and what you're working with is extremely blobby, very undifferentiated density, where you've lost most of your side chain information and even the best resolved regions. The density itself has no features to control the backbone conformation. It's got leads you down all sorts of blind alleys with wrong turns where it appears to connect where it shouldn't and doesn't connect where it should. Loops tend to just disappear entirely, so it makes it very easy to make wrong turns and get yourself lost. And in the case of the insulin receptor structure, there were 3 fibronectin domains that were brand new in this construct after placing the first 3 domains and an antibody with no existing homologs, and they essentially had to be traced by hand. Of course, I knew nothing of that. I just wanted to run simulations of the thing. And in my own defense, I thought I was just following more experienced people at the time, because there were already published papers that had done 70 nanoseconds of MD simulation of this, which at the time was an enormous amount and very, very expensive in CPU time. And I just wanted to use the model doing docking, doing MD to help explain the experiments I've been doing in the wet lab. And they, armed with a lot of naivety and the confident bravado of ignorance, I went along and did a bunch of simulations which fell apart horribly. But looking at the places where they fell apart, I started to realize, okay, some of these things really don't make that much sense, which finally prompted me to really go and find out, well, how to generate a 2FO minus FC map, and actually to learn what 2FO minus FC actually meant. And to cut a long story short, pictured on the right is the spot where I first noticed unstable behavior. And I hope, yeah, just bring up a pointer. I hope you can sort of see, actually starting watching this gray strand down here, you can see it where it jumps out of density and heads off to the right there through a great big positive, negative difference peak, where it fairly clearly should be just coming down here and back up here. And the orange strand here has been threaded through what is actually the disulfide bond density, and should really be just forming a little helix here. And the 2 residues shown here, for just to add a little bit of extra complexity, were actually incorrect in sequence. They dated back to the original sequencing of the insulin receptor from 1985 or thereabouts, where these had been annotated as aspen threonine when they should be valine serine. So a few things going on. And of course, that was extremely deep, almost existential shock to me at the time, just thinking about, well, how much time I had wasted and how much computing time I had wasted and how much time other people had wasted on that, and then thinking about other cases like that, and then thinking, up until this point, I had no idea that this scale of problem could exist. And well, knowing what I know now, that these are actually, take almost any new structure of that resolution from that era, and you're going to find similar problems in it. But anyway, at the time, I figured, okay, I wanted to figure out how did this happen and what could be done to improve it. What it boiled down to for me after a bit of time trying to play around with it is that the core problem really was that the restraints traditionally used in model building, in interactive model building in particular, are really insufficient at low resolutions. They're statistical potentials that are really just controlling very local behavior, the bond lengths, angles, dihedrals, with little or no consideration of non-bonded interactions. And it's the non-bonded interactions that are really controlling everything. And when you have very high resolution data, you can get away with that. But when you're working with these horribly fuzzy maps, they're simply not enough to control things. And then I thought, well, the aim of molecular dynamics, of course, was to try and replicate real-world behavior in the absence of any experimental data. So effectively, like an infinitely low resolution crystal. And about the time I'd started looking at all of this, the people behind the NAMD software had published this idea that they were calling molecular dynamics flexible fitting, where they were taking low resolution cryo-EM maps and using those as biasing potentials to guide the model into the experimental data. But the existing implementations of those suffered from the same problem of a lot of molecular dynamics, in that they were still implicitly assuming that the starting model was essentially correct and just needed sort of stock fitting into the new map. And so I started thinking, okay, what if I made that interactive? And well, a few years later, after a few years of effort and sort of learning a bit of scripting in TCL/TK to work with VMD and NAMD, I had something that worked pretty well to correct that original insulin receptor structure, and that was published in 2015. And this little video is the one that accompanied it. My first, it looks honestly pretty clunky these days, but it was a bit of a revelation for me at the time. And moving on from there, I started thinking about, well, what are the other bottlenecks really holding things back? And you think about the classic cycle of modeling into experimental maps that has been developed over decades. Essentially, what you do, you take your existing model, whatever you have from, say, from molecular replacement and whatever automated model building you've been able to do, you run a refinement of that, generate some new maps. Then you run a validation task, which will generate a bunch of tables of backbones, side chains, clashes, etc. And then that will give you a list of the lowest probability residues first. You work through those tables, you attempt to fix as much as possible, and you hope you fix as much as possible. Then you run another refinement validation, and then it tells you how you did. And then you repeat, as the saying goes, you repeat ad tedium. A refinement is never finished, it's only abandoned. So you work until you decide it's good enough, or someone's going to beat you to the punch, or the pressure to publish becomes too much, essentially, and you decide, okay, I'm done, let's move on. And anyway, what I wanted to ask is, think about this: how much of this could be turned into a continuous integrated process? And the first idea that I played with there was the adding the live Ramachandran markup as the color of the alpha carbons, as you're seeing in this video, that published back in 2016. But at the time, this is basically the last paper I wrote using this sort of prototype, fairly primitive prototype that tool set. I'd really hit a wall in terms of what I could do in that environment, and it both in terms of the software environment and the environment I was working in at the time. And I decided, okay, it's time for a change of scene. And I moved across the world to join Randy Reed's lab and start from scratch on a brand new ground up implementation of these basic ideas. So starting in September 2016, and with version 0.1 of Chimera X, which was just a very little known project by the Chimera team at the time, I came across OpenMM, which is a wonderful molecular dynamics library. It's essentially the only molecular dynamics toolkit out at the moment that I'm aware of that was written first and foremost as a library for developers rather than as a end user tool with the library as the afterthought. And using the Clipper for the map calculations. So I'm using the amber force field, but one very important thing to me that I've always tried to do with this is to make sure that while ISOLDE uses molecular dynamics as its toolkit, it never relies on the user to actually know the nuts and bolts of molecular dynamics. It aims to be simply plug and play as much as possible. When you're working with protein, nucleic acid, your classic N and A-link glycans, all of those sort of things, you should be able to just work with it. And the idea has always been to try and make everything feel like you're working with real atoms as much as you can. So when you tug on things, they're behaving like real atoms. And what you're watching here might be a little bit confusing, but this is one of the built-in tutorials of ISOLDE as it stands today, using a web of distance restraints based on an AlphaFold model to interactively clean up a very old legacy model from the 3 angstrom model from 2007, with many of the same sort of problems as I originally ran into in the insulin receptor, various out of register regions, the sort of thing that would have been a huge pain to rebuild pre-AlphaFold, but now in ISOLDE with these sort of restraints, it's actually a fairly straightforward tutorial that you can get through in the whole model in a few hours. A few features that ISOLDE has. So there's the live Ramachandran and Brodmann validation, of course. So every time the coordinates the coordinates of any atoms in your model change, all the protein backbone and side chains are revalidated. I thought about threading that originally. It's actually happening in the same thread as your as all the graphics, but it ended up being so fast that I've never really seen the need to actually thread it. It's about the cost is roughly a couple of milliseconds per 1,000 residues. So it's amazing how CPUs have come along. Really, there's a similarly there's as Paul mentioned in his talk, one of the things I did fairly early on was dove into Clipper's structure factor calculation code and worked at parallelizing some of the bottlenecks in it across available CPUs and pushing everything into a background thread, so that now the maps can just keep on updating in the background as your model changes. And so they're trying to update as fast as they can. So essentially, when an atom moves, it triggers a background recalculation. When the new maps are ready, they're just popped into place over the top of the existing ones. And if things have changed in the meantime, then they update again. And so you'll see for this model, for example, it's about a little over 1,000 residues. The maps are changing a little bit faster than one update per second. But for smaller models and data sets, it can get very remarkably close to real time, and really quite fun. And so there's I'm not going to go through much more of this. There's a bunch of built-in interactive tutorials that I would really encourage you to try out. The installation is as simple as I can make it in Linux, Mac OS, and Windows. Once you have Chimerix installed, you just go to their menu, tools, more tools, and there's a couple of buttons you have to click, and ISOLDE will just install for you and should be ready to use. And for third-party developers or people who just want to be adventurous, there is a Python API, and that's all available via an interactive Python shell within Chimerix, so that you can actually run things and see what happens directly. And of course, for best performance, because all these simulations do run on a GPU, I've always tried to develop for, well, when I started this project, I was aiming to develop for the hardware that was very high end at the time, which is now fairly commonplace. So you need more or less a good but not great gaming level GPU to get really good performance out of this. So think your the NVIDIA RTX 3060, 70 series GPUs. So some of the lessons I've learned. One of those, so realism is good, can be very good until it's not. And where it becomes a real problem, of course, is when your model isn't yet good enough. Molecular dynamics force fields can become a real pain, or your vanilla molecular dynamics force fields can become a real pain. And the problem, funnily enough, is that improved treatment of non-bonded interactions, because the van der Waals force is extremely unforgiving. When atoms overlap, the energies shoot up very quickly to the sort of energies you'd normally only ever see, like inside the ring of diamond light source, or in a particle accelerator or a nuclear reaction. And the forces that would send atoms flying apart at a good fraction of the speed of light. Now, and in computational terms, what they can very easily do is run the energy right off the top of the limit of single precision, so that minimizers have no gradients to work down. So one of the things that made a huge difference was the introduction of soft core potentials that remove those singularities, that basically level off the energy at small distances, so that it can safely escape those sort of problems. And also, when you're talking about interactive tugging, you tug with the mouse, you don't think you're doing very much, but the force you're actually applying is way beyond anything that's natural, and can very, very easily flip chirality or peptide bonding to cis or trans, unless you add some safety barrier potentials on those dihedrals, which ISOLDE, of course, has. Other thing, so the amber force field is extremely venerable these days, and is very good, and so is charm in many ways, but they're not the final answer to the problems we have in model building and refinement. And there are various reasons for that. One of the more obvious ones, for anyone that's actually used a model directly from ISOLDE and tried to deposit it to the PDB, which I don't recommend, you should still be refining your model, is that you will get lots of red flags for bond and angle outlier RMSDs, simply because there are some small but systematic discrepancies from experimental structures in bond lengths and angles. The sort of things that don't really make a huge amount of practical difference in day-to-day rebuilding, which is why rebuilding in ISOLDE really does work really quite well. But when it comes to refinement, you need to be getting those out. And that's but more importantly than that, these force fields are becoming increasingly unwieldy when it comes to the addition of new chemical entities, for various reasons. But as it stands at the moment, protein, nucleic acid, drug-like ligands are generally quite good and easy to add. New covalently linked residues are really hard and really require someone with experience in molecular dynamics parameterization and to hand tweak things. And anything with exotic elements becomes even harder. Behavior of metals is generally not great, especially any metals with more than a +1 charge, which is why one of those early workarounds, which works much better than it really should. Say early workarounds, early hacks, it works much better than it really should. Every metal ion in ISOLDE is actually +1, because the +2 ions were just the +2 charge was really poorly behaved in implicit solvent. And the implicit solvent treatment itself is good. It's accounting for the presence of water without actually having water there. It's good, but it's not perfect. And so there's a lot of promise here in next generation machine learning force fields and potentials. So the machine learning force field is something that essentially will use a machine learning algorithm to apply your classical molecular dynamics parameters to a model, and then you just run molecular dynamics as you normally would. And the advantage here is that rather than working via the old school approach of individual residue templates, you just feed it your entire molecule as a graph representation, and it gives you parameters back for everything. As long as everything is within the chemical gamut of what it was trained upon, then everything should just work. Machine learning potentials, on the other hand, are where you're using a machine learning algorithm to actually directly calculate forces at every step of your simulation. And those are showing a lot of potential to give us ab initio-like results at much better performance. But the thing about these is that they need to be used with great care, and the problem with them is a problem that we already have in the PDB now, is that it doesn't take too much digging through ligands and unusual residues in the PDB to find some impossible chemistry, like the sort of abstract art you see here on the right, where typically some overzealous software has turned clashes into actual covalent bonds, and then the refinement software has gone along with it and done some interesting things. So the problem with using a machine learning parameterization approach is that, well, it's not going to know about these sort of problems. It's just going to try and give parameters for these and make even more of a mess. So ultimately what this means is that the responsibility is going to be more on developers to actually build in deeper chemical knowledge directly into the model building software to avoid these messes in the first place, to tell the user, because it's easy to blame the user for things like this, but we have to remember that a lot of the models in the PDB are done by people for whom this is the first structure they've ever done. Many people they're biochemists, not necessarily chemists. And especially when you're not actually including hydrogens in your model, especially this one up the top, it's easy to miss that this is actually wrong if you're not really thinking in terms of chemistry. So we need the software to be able to tell us this is wrong. And that is going to be a bit of a hard problem. I have no doubt of that. And existing computational chemistry software is expensive for a reason. But ultimately, I think our biggest bottleneck right now, and the thing, if I was going to start a new project today in computational structural biology, I personally wouldn't be going for improved automatic building right now, because I don't think that's the bottleneck anymore. Because we're hitting the point of diminishing returns there, because what I find more and more is that I spend so much of my time doing essentially this, scrolling end-to-end through a model past the 90 to 95% of residues that are perfectly good to find the one or two that are wrong and fix them. And the reason I'm doing that is because our validation tools really aren't trustworthy enough as they stand. The reason for that is that most of the tools we have are about flagging statistical outliers. And they're good at doing that, but the really insidious problem is that most of the problems that you will find in a model these days in the PDB aren't statistical outliers. They're residues that are within the allowed contours of the Ramachandran plot, the Rodemer contours, etc., but they're still wrong. And we don't have tools that can truly reliably find those. And until we do, the gold standard is going to remain that human eyes and experienced human eyes should see each residue in density at least once. And as long as we have to do that, as long as a human has to go through residue by residue, or should go through residue by residue through the density, there's very clear evidence in the PDB that not as many people do that as they should. It's the improved auto building isn't really going to get us that much further, because when you've got a 95% correct model or a 99% correct model, it's going to take you not that much amount of time. Well, it doesn't take me that much amount of time difference to fix those two, because most of my time is just spent finding the problems rather than actually fixing them. And a little bit of a segue here. People who are at the CCP Spring Symposium will have seen this one, but the meaning of this will become clear in a second. But So way back when, the ancient Greeks assumed that Earth was the center of the universe, with the heavenly bodies revolving in spherical shells around it. That was an understandable initial assumption, but people started to realize that the fit to observations was fairly poor. And so Aristotle
Sorry,
introduced
Sam has fired his bubble gun. I did drop you a message in Slack. Minus 1 minute. So if you want to wrap up real quick, that would be great.
Really quick. Okay. So the point of this was that epicycles, people used epicycles to try and fit these observations to the data and force fit observations to data. And honestly, that's more or less what we're doing today with a lot of the restraints. And I worry that that's what I'm doing sometimes as well. And the worst case of that is this guy from a few years back now, which is passing most of our validation criteria as flying colors, but is disastrously wrong when you look at the details. There's huge areas massively out of register. And so we really need to start rethinking this very, very carefully. Yeah, I'll skip past this. The basic idea of this one is that the reason why we really need to start getting past that the human eyes should see each residue in context at least once is we're starting to see models like this, which at the rate I worked on a ribosome a few years back, you're talking 400 hours of non-stop human time to get through that end to end. It's just not possible, and which is why the details aren't great, and the validation report is almost 5,000 pages long. So concluding, so so these are all the things I've essentially said. So we really need to think about a real step change in validation. I think is a really biggest next step that we need to make before we can really step forward and start making perfect models deposited in the PDB. And that's my acknowledgments. And I do apologize for running over time.
No problem. Thank you very much. So while Lucy sets up, I think we'll have one question, if there is a question to be asked. One at the back. Ben,
Could you say anything about model bias in your program and how it deals with model bias?
So it's a little bit of a tricky one. So ISOLDE has always been mostly about polishing a model that is mostly complete, where model bias tends to be less of a problem than the early stages where you've only got a small proportion of your model in place. But that being said, I do find that just the use of the physical force field really helps with that a lot, because a lot of model bias tends to come from people force fitting things in places where they really don't belong, and the force field just won't allow that. The MD force field will try to push everything back out of density if it really doesn't fit there. So I mean, I can't say anything really quantitative, but ultimately I very rarely see any serious and anything that makes me worry about model bias with working in ISOLDE.
Thank you very much. So if we thank Tristan again.